Welcome to Everything Distributed. Today we are going to talk about consistency models or guarantees in distributed storage. So last time we talked about one of the key challenge in distributed database or distributed storage is that we need to do some kind of coordination because eventually or the ultimate goal is that these different machines, different servers, they should behave as a single entity. But for doing that, then you require lots of communication between servers, and then potentially lots of communication between clients and servers. And then if some of the server is slow or some of the server is very far away, then it's very slow. So how do you do the coordination while maintaining the high performance? That's an ongoing research challenge. Okay, so and then as a reminder, last time we talked about that to study the fundamental, we start with the most simplest version of the database, which is a shared key value pair. You have a key K and value V. And then the API is as simple. You can do a read and write. And intuitively, what is a consistency model? Consistency model is a correctness condition. It tells you that what is the expected relationship between the data items that's stored inside the server and then the result of the operations. So right now we only support two APIs. So that especially when you do the read, what is the correct values that is returned by the database? And then that's something we care about. Okay. And the content of this today is based on two reading. One is a chapter 9 in Martin Sinai's book, and then the other one is from this great article by Dog, which is now data consistency model sometimes very abstract, but he used nice abstraction on an example of baseball to explain that why do we care about different kind of consistency, and then what is the correct usage of different kind of consistency models. So last time we briefly talked about this very client-centric view of consistency. And then today we are actually follow the discussion, but with one more, which is bounded staleness. And so if you remember from last time, the challenge is coordination, and then coordination because that it requires communication. And then usually that when we want to achieve a higher consistency, meaning that the strongest is kind of you use consensus and then you want them to behave as one entity, but we know that this is impossible to achieve consensus. So we say, okay, we cannot do consistency, then we cannot do consensus. So we want to have a one strong notion is that suppose that we have a client. Okay, I'm going to write something, and then usually in the kind of notation wise or illustration, we write this W, where this is the initial invocation point of the operation, and then this is the termination point, meaning that the database tell the client say that, okay, your operation, your value is stored inside the system. So let's say this is T1 and then this is T2. Okay, so that this the client issue W at T1, and then they do some communication inside the machines, and finally at point T2, tell the system tell the client say, okay, it's completed. Then now what the consistency is regarding that, okay, if I have a future reoperation, suppose I have a reoperation that's overlapping with the write, or like I have a read operation that occurs after this W, the write operation, should this read see this write operation? So suppose this write is I update key K to value 1. Okay. Then suppose initially the value is 0. Okay. Then in this case, the consistency tell you that whether this read operation can return 0 or 1. And whether this read operation will return 0 or 1. And depending on your operation, depending on your consistency guarantees, the overlapping operation or like the operation happen in the future, but that may touch a different set of machines. They may return different things. Okay. And then that's one of the challenge when you arguing with database, because that when we do distributed database, that every machines and every client, they only have a partial view. And then that's why it's not very intuitive. Okay, now let's look at some of the common, the one of the biggest principles that the stronger the consistency is, then the longer the latency and lower the performance. So why is that? So usually that when we want to require strong consistency, when the writer that try to write some value, somehow that it needs to contact with at least a core of servers. And then whenever you need to contact more servers and then wait for more acknowledgement or replies, it's getting slower. And then that's why that the stronger the consistency, the slower the performance. And then there are tons of different consistency. And then the idea is that how do I find the consistency that satisfies my need for writing my application correctly and precisely, while maintaining the consistency as weaker as possible? Because the weaker it is, in theory, you should have a higher performance. Okay, so last time we briefly talked about the strong consistency, meaning that when you're doing a read, it should observe all the values that are written by all the previous writes that have already completed. So this completed is a key. And then eventual consistency is like kind of on the other spectrum, which is one of the weakest one. But sometimes this is very confusing because eventual there are many different interpretations. And here we adopt one of the simplest one is that let's assume that replica or the server eventually receive all the right operations. And then somehow if the clients, there's no more writers, meaning that there's no new updates that's issued to the system, then eventually the read operation will be able to return the object, or like in this case the key's latest value. So remember that in distributed computing, a key value pair, sometimes we also call it a read-write object. So when you read articles, sometimes you find both terms. Okay. And then last time we talked about read or write. We also talked about monotonic reads, and we also talked about consistent prefix, and all of them actually belong to eventual consistency. And then the final one that we introduced today, it's also mentioned in Doc's articles called bounded staleness. It's that suppose I have a write operation, and then I have another read operation. And then by bounded staleness is that I have a threshold. If like this t is above the threshold, this t is longer than the threshold, then this read must always return this write operation. However, if like this t is very small, like maybe say 1 millisecond, then basically you don't really have time to propagate your write values. So realistically, you should not expect the read operation to be able to return the value returned by this write. Okay, so that's the notion of bounded staleness. And then in arguing this kind of distributed system, you will constantly find yourself into like trading off between performance, reliability, or fault tolerance, or like consistency guarantee. Okay. So that's all the consistency model that we are going to focus on today. And then dog use this baseball as a very simple application. And in case you don't know what baseball is, the Wikipedia provide enough detail for you to understand what we are going to talk about next. Although in Dog's article, he also mentioned like the essential knowledge that you need to know, and he also provide codes for you to read. Okay. And here the assumption for the baseball is that we want to write an application that keep track of the scores. So we have database that have like two columns or like two key value pairs. One is for the to keep track of visitor score, say VS, and then like home score, let's say home HS, where the key is simply VS and HS. And initially, each item is initialized to 0, 0 because nobody scored. And then in baseball, it proceeds in kinds of runs where we call it an inning. And in the inning, let's say that the visitor, they will bat first and then home bats. So like it has an upper inning and then bottom inning. And then the game has a total of 9 innings. And in our application, you only need to know these notions. And now suppose that a referee that he or she wants to update like visitor score. The way it does is that it doesn't really keep track on the score by he or herself. Then it's kind of stateless. So the referee always reach out to database, say that, hey, what is the current score? Reads from the VS, and then it will increment by 1, and then write it back to VS. Okay, so that's a very simple application. And for all the other rows, they simply read from the database. Okay, so once you are comfortable with the application and then comfortable with the consistency model that we introduced in the previous slide and also in Doc's article, now here are the questions for you. Suppose that we have referee or official scorekeepers. Then the main job is to update and maintain the scores for both visitors and then the home teams. And to simplify our life, we assume that there is only a single writer. So only one person who will does this update. So remember, how do we update it? We read the value from database and increment it by 1 and then write back to yes. So in this case, what would be the consistency model that we need in order to ensure correctness? And then you may say, okay, we need strong consistency, and then that's correct, because that when we do the read, we always want to have the most recent data. That is the previous write, right? Because if this is not the most recent version, then you always increment by 1 right back. You may replace some of the scores, which is not correct in our semantics, okay? Then the next one is to think about that. Is this the weakest consistency model that we could use? And the answer is no, because if we rely on the application scenario or the domain knowledge, actually we know that, hey, there's only one referee or only one official scorekeeper, so that whenever you do this read, you can always require read my write consistency, because it's always it will always ensures that you read your previous write operation, which is the most recent data score. Okay, so that's one example of like how you use the application scenario or domain knowledge to simplify or to weaken your consistency. And one of the exercise for you is that what if you have multiple readers? Because it's possible that multiple writers, then if multiple writers try to update at the same time and then you use only read my write, would that succeed? Or what else do we need to do? Okay. And then the other one is umpire, and he or she official the game. And most of the cases that they don't really need to know the score. oops, sorry. Then one thing that they need to do is that at the bottom of the ninth inning, they need to decide that whether the home team still need to play the bottom inning, because that if the home team is already winning, and then in the bottom inning, that it's a home team's turn to hit to bet. And then since the visitor can never score more points in the bottom of the inning, so that if that's the case, then the game is like complete. Okay. So what kind of consistency that do they need? And then, sorry, I already showed the answer. It's a strong consistency, because you always need to make sure that you have the most recent score, and that's why you need a strong consistency. And then the next one is a radio reporter. Suppose that every 20 minutes or every 30 minutes, they announce the score over the radio. But one requirement is that there should not be any artificial arbitrary scores, and then more concretely, meaning that I want to have a score X and score Y that really occurs at some point of time. So think about your database system. If you use eventual consistency, that it's possible that you read some scores that never occur in history. Okay, so that's not good. Then what kind of consistency that the weakest consistency that the radio reporter that need to know? And then in order to kind of answer this question, you will want to remind yourself about that there's one certain consistency model that require you to require the reader to observe a consistent sequence of a right operation. And then for that, it's a consistent prefix. So intuitively, what consistent prefix means is that the right operation, they always occur the certain sequence that really happen at some point of time in history. But by this self is actually not enough for radio reporter, because it's possible that at first it's consistent and say, okay, it's a 5-0 game now, but after 10 minutes or after 20 minutes, he or she read again, you find out that the score is 3-0, you say, okay, it's 3-0. Then the audience will get confused, right? So why is the score decreased? So in order to avoid this EOK scenario, you also need to have monotonic read, meaning that every time you read, the sequence that you are reading should actually grow. You should see newer and newer version. Okay. So it's very interesting that this consistency model is especially for all these different kind of eventual consistency. Sometimes you need to require 2 or more in order to make sure your application semantics is respected or satisfied. And then for this one, actually there's another combination that's okay, which again, you want to have a consistent prefix because you want a score that's really occur at some point of time. And then you can also have a bounded staleness. And then that's, again, it's based on the semantics or the applications scenario for radio reporter. So because for radio reporter, you can never kind of broadcast the score too often. So most of the time you broadcast it maybe 10 minutes, 20 minutes, or 30 minutes. So for this bounded staleness, you can always say that, okay, I want the most recent data that's within 10 minutes bound or 10 minutes threshold, and then that will suffice so that you can always read the version that's more recent than your previous read. Okay. So now let's look at the final one, which is sports writer. And for sports writer, at least based on Doc's observations, sport writer, they only check the scores that's after maybe 1 hour or 2 hours after the game is completed. So in this case, you only need to know the final score. Then what will the consistency model that will suffice this application? And then, yeah, similar to a radio broadcaster case, he or she only needs the bounded staleness, especially if he or she know that the game has already terminated or has already completed for a very long time. Okay. And then in the article, Doug also mentioned that, okay, for some stat watcher or statistician, then what kind of consistency they need to do. And then it's a very fun read. Yeah, if you're interested in the application for consistency model, you can read it. And then you might say that, oh, this is just a toy example. It's not really useful. But actually, that in Microsoft, they a very smart group of people, they extend this notion and then integrate it into real system. So basically, they say that, okay, I have this so many different kind of consistency, and each of them has a different kind of latency guarantees and performance. So they say that, why do I have this kind of different SLA, service level agreement, and then as a user, as a client, we can specify the consistency guarantee that we need. And then basically it allows the freedom for the client to play with a consistency and latency or performance trade-off. And yeah, so that's a very nice paper. And then you can see that in practice, in real world system, how do they trade in off this consistency and other things. Okay, then. So that's all for today. The takeaway is that we revisit the consistency model, and then we discuss 6 consistency models and then apply into the baseball application. And one thing to remember is that consistency, of course, that we want it to be stronger, but not often that means that we need to suffer from lower performance. So what is the correct model to use while we don't lose too much performance? That's always the challenge of using this kind of distributed storage. Okay, that's all. Thank you.